My name is Alex Fishman, representing Ravello Systems, and I'm going to present our solution of a cloud built entirely on the top of public cloud infrastructure. So actually, our solution is pretty much similar to the previous speaker, with one crucial difference that we actually built a working cloud on top of public cloud infrastructure, like Amazon EC2. So I'm going to present how we did it, how we actually managed to build such a cloud. So again, our cloud is fully functional cloud that, instead of relying on physical hardware, utilizes existing public cloud infrastructure. And the building blocks of our virtual cloud are nested hypervisor, which we developed specifically for the purpose of using the public cloud VMs as a host for running level 2 guest VMs. We also built a layer 2 overlay network on top of a public cloud provider network. We have another component which is used for storing and uploading your own images for this cloud, and we also have a management system for actually provisioning VMs. Just a few words about our hypervisor. Our hypervisor actually provides a hardware abstraction layer to level 2 VMs. So our cloud can load any kind of images, including VMDKs. For example, if you have your private data center running ESX, you can load your own VMDKs images on top of our cloud, and you don't need to modify any device drivers, for example, because we implemented the hardware abstraction layer. So in the next few slides, I will talk about implementation details and show you our solution in few more details. Actually, this picture depicts the components of our cloud. As you can see, on each public cloud VM, we install a small, thin provisional layer which packs in a hypervisor, hardware abstraction layer, storage, and also network modules. We also have an image store and a management server which provides the APIs. So this cloud is fully functional. So you actually can upload your own VMDK images into image store and then just fire up some VMs. And what is also, I must mention that the VMs that you can launch with our solution can run on top of any cloud, any public cloud like Amazon or Rackspace or HP without any modification. So our container provides a heterogeneous platform for running your VM image. Now, a few words about motivation, why we want to build such a solution. As you know, many companies already deploy virtualization on premise and would like to take advantage of elasticity that a public cloud can offer. And you know, when you run in your private data center, you need to prepare your data center for peaks. So when you run in the public cloud, you have this kind of elasticity that you can just launch up VMs and you don't need to worry about workloads. So this is the case why we wanted to build such a cloud. But sometimes it is very hard, and it can be very tricky to move your workloads from a private data center into a public cloud. And this is why we built our own cloud. Now, I want to talk a few words about why transition from a private data center into public cloud can be tricky. First of all, as you know, you cannot run your own VM images. Almost always when, for example, if you run on Amazon or Rackspace or HP Cloud, you have to rebuild your images from scratch, and often this leads to a single provider lock-in. Additionally, not every cloud provider supports your own VM images. For example, on some cloud providers you cannot run Windows, or on other providers you cannot run your network appliance. For example, if you want to run some kind of complicated firewall appliance, you often cannot run it. Also, as you know, there are different incompatible APIs between EC2 and other clouds. Some use Eucalyptus, as in case of EC2. Others use OpenStack flavors, which are also incompatible between each other. Microsoft uses its own Azure API, so it's quite hard to move from one cloud to another. Now, I must also mention difference with virtualization technologies. And as you can see, there are two types of virtualization technologies. One is called para-virtualization, or PV, and the second type is called hardware virtualization, or HVM. Para-virtualization means that a guest VM must be modified in order to be run on top of hypervisor. HVM is a more modern approach and doesn't require modification of the kernel. This HVM approach is implemented by CPUs, by modern CPUs that provide virtualization extensions to a hypervisor. So with a hardware virtualization, most of the code, so with hardware virtualization, CPU does most of the work and runs the VM on silicon. Now, just a little bit about para-virtualization and why does it require guest modification. In para-virtualization technology, the guest kernel usually runs on user space or ring 3. And that means it is not allowed to execute privileged instructions. So instead of executing privileged instructions, the guest would ask the hypervisor to perform the desired action. And this interface is called hypercalls. And this must be implemented by guest operating systems. Therefore, guest kernel requires modification to be able to be run on such hypervisor. By the way, examples of such hypervisors, that support para-virtualization is Xen. And as you know, Xen is used exclusively by Amazon and also by Rackspace. So we cannot ignore Xen and must support it if you want to run our nested cloud on top of Amazon, for example. Now, I also must mention other issues like virtual hardware, which is exposed to VMs, different and differ from hypervisor to hypervisor. Each hypervisor exposes a different set of virtualized hardware. So if you run on top of Xen, you would see your VM would see one set of hardware, and if you run on top of KVM, you will see a different set of virtual hardware. Now, if you want to move a VM from one hypervisor to another, it is similar to taking a hard disk from one PC and moving it to another PC and hope it will boot up. And this is often not the case. So moving a virtual machine from one hypervisor to another or from one cloud to another is pretty hard and it can be tricky. So let's see how our approach solves this. So actually, in the heart of our solution is nested hypervisor that we developed. And I would like to go into more details. Why do we need a new hypervisor, and also talk about some implementation details. Now, again, many people ask, why do we need yet another hypervisor? And in a few moments, I'm going to answer this question. But first, let's talk about nested virtualization. First of all, nested virtualization is not new and already implemented by KVM and ESX, as it was mentioned by the previous speaker. But it requires CPU support, and specifically the feature which is called EPT, or Extended Page Table, which is implemented by Intel, or in AMD it is called nested paging, or NP. But the most important thing, and this is probably the key to why public clouds do not support nested virtualization, is because the host must be configured in a very specific way. So the hypervisor must expose those virtualization features of the CPU to level 1 VM. Now, remember that what we want to do is we want to create our cloud, our nested cloud on top of a public cloud infrastructure. But public cloud do not support nested virtualization. And this is mostly because they don't require to do so, but also because such support would be very hard, if not impossible. Many clouds, if you take, for example, Amazon, they have a mix of older and new hardware, and not always older hardware support nested virtualization at all. Also, if you take a look at Amazon, they have different hypervisor versions which they run, and it is it is impossible to would be impossible for them to enable a nested virtualization. So precisely of that limitations, we developed a new hypervisor which is capable to run on top of any other hypervisor. And our hypervisor doesn't use hardware extensions at all. But our hypervisor do allow to execute unmodified guest VMs. And if you ask how we do it by utilizing the technique which is called dynamic binary translation. And this technique was not invented by us, but by VMware, and we just took it to the next step and took it to a public cloud. Again, if you look at this picture actually depicts how HVX hypervisor architecture. As you can see on the bottom, we have a cloud VM hardware provided by the cloud hypervisor. For example, if you run on Xen, we can see Xen hardware or Xen devices. If we run on top of KVM, we can see KVM devices. On top of that, we have our virtualization layer, which includes Linux, and on top of that, we load our hypervisor, which we call HVX. And our hypervisor, as I already said, provides a completely different hardware set to the guest VM, what we run on top of it. Just to give you a few highlights, as I already mentioned, we implemented our own virtual hardware set, and with this hardware set this virtual hardware that we implemented actually quite a few ESX devices, so we can run unmodified VMDKs on top of our hypervisor, on top of public cloud. And if I have enough time, I will show you a small demo including this feature. We also allow CPU and memory overcommit, or we also do consolidation. Consolidation means that we can run several level 2 guest VMs on top of one single host VM. With CPU and memory overcommit, we rely on the fact that most VMs, similarly to their physical counterparts, are running mostly idle. So underutilized. So it is possible to overcommit without degrading performance significantly. We also implemented advanced features such as live migration. So it is possible to move a VM from one cloud to another cloud, another public cloud, almost seamlessly. Now I want to talk a little bit about the dynamic binary translation. This slide is quite technical, but again, I want to say a few words about it because it is quite difficult to implement such technique. As I already said, instead of relying on hardware extensions provided by the CPU, we implemented binary translation technique. This technique, as I already mentioned, was first utilized by VMware hypervisor for virtualizing x86 platform. Since hardware extensions were introduced, VMware abandoned this technique, for hardware extensions. So, how binary translation actually works? First of all, we read and recompile the guested kernel code so it can be executed on ring 3 of the CPU or on the user space. In such a way that we must replace privileged instructions with a simulation code that alters a shadow CPU state instead of the physical one. We repeat this algorithm until we see a jump to another code. So at this point, we insert jump instruction back to HVX, so back to the compiler, so the controller returns back, and then we repeat the process of recompilation and again and again. And this is how we run actually the guest VM. Now, we also implemented many optimizations to make sure that our performance, we get minimum performance penalty. Just to mention a few of our optimizations, user space code of guest VM is not compiled and instead executed directly on the CPU itself. So we get quite good benchmarks that I will show you later. Now, this is regarding the network. This is also the crucial stuff that we need to make sure works. We implemented our own overlay network by using custom algorithm. Our custom algorithm is quite similar to GRE. The reason for not taking existing standards such as GRE itself is the limitation of cloud providers. For example, in many cloud providers, only TCP and UDP protocols are supported. And if you know, GRE cannot be used because it uses a different IP protocols. Again, with VXLAN, we cannot do VXLAN because it requires multicast, which is also not supported in any cloud provider. So we ended up by implementing our own protocol. Again, our tunneling protocol is our protocol is quite similar to GRE, but instead of using IP, it uses UDP. We establish tunnels from each node to each node on the same VLAN, and since our tunnels are completely stateless, our solution is quite scalable. We tested our solution on hundreds of VMs running on the same VLAN, and we didn't see any significant performance degradation. We can also secure our layer 2 network by running it inside IPsec. I must also say that we provide additional services to guest VMs such as DNS, DHCP, and routing. And also our services are completely distributed. We run, each of the services are running inside the container itself. So if one host VM fails, our network is still up and running without any problems. Now, another component what we have is image store. As I already said, image store is used to upload your own images into our image store. Our image store runs entirely on a public cloud as well. It supports we support many different backends, including object stores such as Amazon S3 and Rackspace Cloud Files, but we can also use the regular block devices or NFS attached volumes. The store contains VM images that user uploads to our cloud. And if you look at VM image, it consists of disk data, and which can be in VMDK, QCOW, or RAW format. And also we have a metadata describing the VM itself, how many CPUs and what devices does it contain, and so on. I want to say a few words about the actual process of running a guest VM. First, we must provision a public host VM from a public cloud. After that, we install our provisional layer on top of this VM. This layer includes Linux kernel, hypervisor, and also network and storage components. Our storage module includes a connector to the image store. We implemented it by using Fuse, which is a user space file system. So to Linux, the image store looks like a file system, and the backend can be S3 or a Cloud Files or any other backend that we support. So after that, after the create networking and mount the guest image, we can run the VM itself by using the provided data. So maybe I should also mention a few words about the image chain or snapshotting. Our image store contains read-only VM images only. When we create a new snapshot, when we provision a new VM, we create a new snapshot of that VM image, which is stored on a local disk. And all the writes, all the new disk data goes to this local disk. If we want, we can upload this new snapshot into the image store, and we have a new VM. So I'm going to skip this slide, and actually I want to have a few words about the performance of our hypervisor. This slide describes the numbers that we measured of the benchmarks that we run and we measured of the HVX hypervisor. Just a little bit about a methodology we employ to get these numbers. First of all, we used a Linux test suite for running synthetic benchmarks such as Apache, OpenSSL, PGBench, and PHP. We also used a kernel build and measured how much time it takes to build a kernel, and we used iPerf for network testing. So in order to measure performance, we created 3 VM instances. One is on EC2 in the Xen PV context. The second one is EC2 in the Xen HVM context, and one is in the HP Cloud on KVM context. On each instance, we ran benchmarks twice, one on the bottom or level 1 VM, and another on level 2 VM with HVX installed. The results of the first one is our baseline for comparing with the results of HVX. So if we go to these slides, you can see actually the results. So what I can say about these numbers. We can actually, the 100% is the base results without HVX on the same image. So we can divide the benchmarks into 3 groups. One is CPU-bound workloads, and the second one is kernel-bound workloads, and also we have mixed workloads. As you can see, the CPU-bound workloads such as OpenSSL and PyBench and what else? And PHP bench perform almost identically to their native counterparts, so there is almost no performance penalty. We can explain this by the reason that we execute user space code directly on the CPU without a binary translation. If you look at the kernel-bound workloads such as Apache and PGBench, we can see that there is performance penalty, which is related to HVX. Although the penalty looks significant, it's actually on par with with other hypervisors. When you run benchmarks on other hypervisors and compare it to bare metal, you will see a similar performance penalty. And the third time of benchmarks is actually is mixed benchmarks such as kernel compilation, which the results is somewhere in the middle. Okay, maybe I have time for a short demo, and I can show you a VM, Windows 2008 running on a Amazon PV context. So let's look at it. I have these VMs here. As you can see, it is running in parallel virtualization context. Okay. And when I connect to this VM, I can see this is actually Windows 2008, and as you can see, it uses VMware PV SCSI controller, so it runs with its native disk device controller. So it's like I took a VMDK from my ESX data center, and then I just put it into our cloud, and I just launched it I launched an instance in the EC2, so I got this Windows up and running. Okay. Thank you. Any questions? Yes, please.
How does that work compared to QEMU? They are
Well, it QMU, yeah. So QMU is very slow. You know, it does stuff in user space, so you can't run any real workloads on top of QMU. We have a real hypervisor which is quite capable, and then the performance is quite good. So it's much better than QMU.
I read just about QMU. QMU is a platform to run ability to emulate one platform on another. So what's happening if QMU is translated code? It does not write to keep the code native. So it translates into different blocks. What's happening in QMU is the user space as well get compiled. Plus the addition, the must overhead of QMU is the fact that because QMU is totally in user space, unlike HVX that use hardware MMU, each memory access need to go through a virtual software virtual TLB. So what's happened is that QMU for each virtual memory access and have to go on the page table and translate the address. So that makes QMU very small compared to virtualized.
This is very slow, yeah. Other questions? Yes, please.
Yes, Abel Gordon from IBM Research. One question related to overcommit. You mentioned in your third slide that you can overcommit resources.
Yes.
I was wondering if you're looking to what will happen if both the L0 hypervisor and the L1 hypervisor overcommit simultaneously.
That's an interesting question. I really don't have an answer for that. In the cloud, by the way, there is no overcommit. So in the public clouds that we know, there is no overcommit. At least not there is no memory overcommit. So things should run pretty smoothly, in my opinion.
Amazon guarantee the Amazon it's split the memory and does not run memory overcommit at all. Amazon is built on Zen.
Okay,
so
just was asking if you have considered what will happen if
we have considered it.
And also you have CPU and I/O and all this stuff. That's not just memory.
We have page sharing, we have swapping, and that's our ability to memory overcommit.
Do I have time for another question?
Yes, and then how does HVX compare to Zen Blanket?
Zen Blanket is basically what they did was to take in Zen PV. What happened at the hardest thing here is to run on platforms that does not expose virtualization extensions. So what's happened is that Zen as a Zen PV, it's allowed to run on an unvirtualized platform because it required the guest to be modified to run on Zen. So what they did was to run on Zen HVM machines. So the Zen HVM machines in Amazon expose normal hardware extension of normal hardware abstraction of x86. On top of that, they ran Zen. And then what happened is that you got to run only Zen para-virtualized guest on this. With our solution, you can run any x86 32 bits, 64 bits, Windows, Linux, SMP, or whatever you want, even Solaris, on our solution.
On top of any hypervisor, not only Zen, but also KVM, also Microsoft Azure. Yes, please.
Is it possible in 3 or 5 years later we have nested hypervisor if this works?
I guess so. Yeah, it can work. Yes.
Okay. Yeah. From the performance perspective,
yes.
Have you analyzed or compared how your approach compares to hardware with nested virtualization support with hardware extensions like the Turtles project?
Yes. Okay. Okay. First of all, our solution is very similar from a performance point of view to VMware ES6 when with dynamic translation. We have advantage over nested hypervisors that use VMX from the fact that nested hypervisor today cause a lot of VM exits on each VM exit that they receive. The average VM exit of level 2 hypervisor cause 10 VM exits on the lower hypervisor. This due to the fact that the upper hypervisor need to read the virtual machine control state. Now, there will be some extensions that Intel will add that will make it faster. No one will ever be able to beat the hardware. It will take time. Another thing, another advantage that we have is that our page table hierarchy is faster for user space than normal hypervisor, for example, nested KVM, because nested KVM use extended page table where the EPT is have 2 layers, one for that, and we got it direct. So I would say that in the future, as Intel will add more and more features to solve this, in the end, hardware will be faster. But for now, we are much faster than other hypervisors due to the VM exit issues.
Okay, so first of all, there is today shadow VMC support in nested. So all the
Intel
access to the VM's control
Intel just
will be removed. And so I'm not convinced, from the performance perspective, that you will perform better. But just was asking if you really have some numbers on how.
First of all,
Okay, yeah.
Yeah. Please approach us later.
Thank you.
Thank you.